We're continuing with Chapter 1 in the geometry textbook. In this video, we're going to go through section 1.5, which is an introduction to geometric proof. So as I've mentioned in previous videos, in this course, when it comes to topics like geometric proofs and, strict notation, things like that, this channel is not designed for math majors. When it comes to the math on this channel, this is more for people who are going to apply mathematics in their respective fields, engineering, etc. Engineering, biology, chemistry, etc., business. And so the goal of this course is to really understand the geometrical concepts. But as far as learning how to do rigorous proofs, in my opinion, that's something that's more for math majors to really understand. However, we're still going to go ahead and read through all of these sections just to get a sense for it. So, all right, to believe certain geometric principles, it is necessary to have proof. This section introduces some guidelines for establishing the proof of these geometric properties. Several examples are offered to help you develop your own proofs. In the beginning, the form of proof will be a two-column proof with statements in the left column and reasons in the right column. But where do the statements and reasons come from? To deal with this question, you must ask what is known, given, and why the conclusion, which you're trying to prove, should follow from this information. In correctly piecing together a proof, you will usually scratch out several conclusions, discarding some and reordering the rest. Each conclusion must be justified by citing the given, or hypothesis, a previously stated definition or postulate, or a theorem previously proved. Selected properties from algebra are often used as reasons to justify statements. For instance, we must use the addition property of equality to justify adding the same number to each side of an equation. Reasons found in a proof often include the properties found in tables 1.5 and 1.6 on the next page. So, okay, let's make sure we understand this. So a two-column proof, statements in the left column and reasons in the right column. So you're going to make a statement in the left column and then give a reason for that statement in the right column. Where do the statements and reasons come from? So to deal with this question, you must ask what is known, given. So what do you know? And then why the conclusion should follow from this information. In correctly piecing together a proof, you will usually scratch out several conclusions, discarding some and reordering the rest. Each conclusion must be justified by citing the given, which is the hypothesis, a previously stated definition or postulate, or a theorem previously proved. Okay, so let's keep going, and we'll get a better sense of this as we go. So we're going to so here's the table where you'll make a statement in the left column, and these are some reasons you'll give for that statement. They're giving us some examples here. Properties of equality, so addition property of equality, subtraction, multiplication, division. Yeah, you could do the same thing to both sides of an equation, and it doesn't change the equation. But when dividing both sides by something, you can't divide by 0. Okay? Now, these aren't the only reasons you can use for making a statement, but they're just giving an example here. As we discover in example 1, some properties can be used interchangeably. All right, which property of equality justifies each conclusion? So if 2x minus 3 is equal to 7, then 2x is equal to 10. That's the addition property of equality. If 2x is equal to 10, then x is equal to 5. That's the division property of equality, or the multiplication. So yeah, you could say either or. You could divide both sides by 2 or multiply both sides by 1/2. And that's what they meant by interchange. You can use properties interchangeably. Okay, further, here's more properties of equality. The reflexive property, symmetric property, distributive property, substitution property. If A is equal to B, then A replaces B in the equation. Transitive property. Yes, I mean, these seem obvious to us. But if you're doing an official math proof, I mean, you have to be rigorous. You have to be, every detail needs to be accounted for. So, but we know, like, if you have A is equal to B and B is equal to C, then A is equal to C. And we would state that I guess not, that wouldn't be the reflexive property. That would be a combination of the reflexive and the symmetric property. So, but you have to be rigorous though. But I mean, like, it's like if you're doing an applied math problem in engineering or whatever, you don't need to constantly be stating the properties you're using. You know, you're not going to need to be, unless you're trying to prove something, but you're not going to be doing any proofs. As people who apply math in their fields don't do math proofs. The math proofs are done by the mathematicians, and then once they're proven, then we use what they found to solve problems. Right now, mathematicians are trying to advance math. They're going through all kind of rigorous proofs, and then, you know, once a subject is rigorously proven with theorems and stuff, and it's rock solid, something that's maybe more advanced than calculus, then it'll start to permeate into the applied math. It's already been proven and established and accepted. Before considering geometric proof, we study algebraic proof in examples 2 and 3. Okay, so before we start geometric proofs, we're going to look at algebraic proofs. Each statement in the proof is supported by the reason why we can make that statement or the claim. The first claim in the proof is the given statement, and the sentence of the sequence of steps must conclude with a final statement representing the claim to be proved, called the proof statement. So you start, the first statement in a proof is going to be the given statement. You're stating what the information you have, and then you're going to have a sequence of proofs, and then at the end you're going to make the final proof statement, which is what the whole point of the proof is. You're trying to prove to the reader or whoever, yourself, whatever, that the proof statement is true. That's the goal of the proof. In example 2, we construct the algebraic proof of the claim: if 2x minus 3 is equal to 7, then x is equal to 5, where P represents the statement and R represents the... So P represents the statement 2x minus 3 is equal to 7, and R represents x is equal to 5. The theorem, R is the proof statement. The theorem has the form if P then R. We also use the letter Q in the name to name the intermediate conclusion 2x is equal to 10. Using the letters P, Q, and R, we show the logical development for the proof at the left. This logical format will not be provided in future proofs. So let's just take a look at the example here. So given that we're given this, now we want to prove this, starting here. So I think the idea of the given is that the given is true because that's what we're given. It's true because it's a statement. Or not a statement, but it's a, I can give you the hardest math problem in the history of the world. That problem is true. There's nothing, I don't have to prove that. Or it's kind of like a postulate, I guess. I just wrote it down and showed it to you. So given this, 2x minus 3 is equal to 7. Okay. Now I want to prove to you that if this is the case, then x must equal 5. So, okay, let's see. Now I can add the same thing. So this is true. If this is true, if 2x minus 3 is equal to 7, if that's true, then this is also true based on the addition property of equality. Then 2x is equal to 10 based on substitution. What does that mean? Didn't you just simplify this? So I'm not sure what they're talking about there. But then the division property of equality, you divide both sides by 2, and then finally R by substitution. So let's come back. So, okay, the substitution property, if A equals B, then A replaces B in any equation. Yeah. So, okay. What they're saying is that A is like 2x minus 3 plus 3. And B is equal to 2x. But A is equal to B, so you can replace... What they're doing is they're replacing 2x minus 3 plus 3 with 2x. And they're replacing 7 plus 3 with 10. Which, again, seems so trivial, but, they have to be very rigorous. That's what they mean by that. 2x divided by 2 is equal to x. They're making the substitution. Since you have 2x divided by 2 is equal to 10 divided by 2. Well, since 2x divided by 2 is equal to x, then they just replace 2x divided by 2 with x. Since 10 divided by 2 is equal to 5, they replace 10 divided by 2 with 5. All right, study example 3. Then cover the reasons and provide the reason for each statement. In turn, with statements covered, find the statement corresponding to each reason. So, okay, given this, prove this. So they use, okay, we're given this, then they use the distributive property, then substitution, then the addition property, then the division property. So, yeah, that's all makes sense based on what we just did in example 2. Note, alternatively, step 5 could use the reason multiplication property of equality, multiplying both sides by 1/2. Yep. Note 2, the 5th step in the final is the final step because the prove statement, x equals 6, has been made and justified. Yeah, we're given something and we want to prove this. So once you make the final statement, which is the prove statement, and give the reason for it, then you're done. But you have to get there with these intermediate statements and reasons. The discover activity at the left suggests that formal geometric proofs also exist. The typical format for a problem requiring geometric proof is, so they're talking about this here. In the diagram, the wooden trim pieces are mitered, cut at an angle, to be equal and to form a right angle when placed together. Use the properties of algebra to explain why the measures of angle 1 and angle 2 are both 45 degrees. What you have done is an informal proof. So yeah, I mean, you need geometric proofs that make sense. Why not? Just like you do in any math. So the typical format for a problem requiring geometric proof is given and prove and with a drawing. Yeah, when it comes to geometry, you'll most of the time need a drawing. Consider the problem. So A hyphen P hyphen B. So given that A, P, and B are collinear points with P between A and B on segment AB, shown here, prove that AP is equal to AB minus PB. All right, first consider the drawing, this drawing, and relate it to any additional information described by the given. Then consider the prove statement. Do you understand the claim and does it seem reasonable? Yeah, so there's different postulates before where we can show that there's postulates that state that if you have collinear points, then you can sum those segment lengths and get the total length of the entire segment. Yeah, so to me, this is completely valid, and this can be proven, but let's see the mechanics of how they do it. What they're saying here is that length of AP plus length of, they're saying the length of AP is equal to the length of AB minus the length of PB. That makes sense. If you take the entire length of AB and then you remove this, you're left with the length of AP. And that's just based on, it was like postulates about the lengths of line segments with intermediate points. We also did that same idea with adjacent angles. If it seems reasonable, intermediate claims can be ordered and supported to form the statements of the proof. Because a proof must begin with the given and conclude with the proof. The proof of the preceding problem has this form. So, okay, you have statements, reasons. You're going to start with the given statement, because they have to give us something to start with, or else it's like it doesn't make any sense, you know. But givens are easy. I can give you anything. Anybody can make a given. But then from that given, we're gonna have a bunch of reasons or statements and reasons, and then we want to end with the proof statement and the reason for the proof. So it's just like what we just did with the algebra proof. To construct a preceding proof, you must deduce from the drawing in the given that AP plus PB is equal to AB. Yeah, exactly. And then you could use the subtraction property of equality and you're done. Yeah, the complete proof problem will have the appearance of example 4, which follows the first of several strategy for proof features used in this textbook. So, yeah, this statement here, exactly, this AP plus PB is equal to AB, that was a postulate that we learned. So I'm assuming they're going to state that postulate, and then that's it. Then you just use the subtraction property of equality. So strategy for proof, the first line of proof General rule, the first statement of the proof includes the given information. Also, the first reason is given. Oh, yeah. Yeah, the first reason is given. You include the given information, and then put, for the reason, you put given. Yeah. Illustration, see the first line in the proof, example 4. Yeah. Yeah. So we're given this, like that's what we're given. Observe this. Okay, so we're given that we have a line segment. We've got a line segment A, B, and so there's 3 points, A, P, and B. They're all collinear. We learned this notation before. A hyphen P hyphen B. P is between A and B, not necessarily like a midpoint or anything, just between A and B. And AB is a line segment. Okay, and there's the figure. Now we want to prove that AP is equal to AB. The length of AP is equal to the length of AB minus the length of PB. So we just rewrite the what we're given as a statement and put given. And the second statement is, the segment addition postulate. That we know that AP plus PB is equal to AB. And then from there, just subtract both sides by PB, and you're done. And that's with the subtraction property of equality. Okay. Some properties of inequality are useful in geometric proof. Okay. Yeah. So properties of inequalities are, if you remember from algebra, they're exactly the same as the properties of equality in every way, except for the fact that if you're multiplying or dividing both sides by a negative number, you flip the inequality. But everything else is the same. So there's the addition property of inequality. It's the same thing. Addition property of inequality. No difference than regular equalities. All right, sample proofs. Consider figure 1.56 in this problem. So, okay, here's, you could write this as M hyphen N hyphen P hyphen Q on segment MQ. That's how you could write that. So we're given that MN, the length of MN is greater than the length of PQ. Prove that MP is greater than NQ. All right. To understand the situation, first study the drawing, figure 1.56, and the related given. Then read the proof with reference to the drawing. What may be confusing here is that the given involves MN and PQ, whereas the proof involves MP and NQ. However, this is easily remedied through the addition of NP to each side of the inequality. Okay. So, all right, here we go. Let's see how they do this. So, given that MN is greater than PQ, prove that MP is greater than NQ. So, it's kind of confusing because I feel like we're also, they're going to put given and put MN is greater than PQ, but aren't we also given this? M, N, P, Q on segment MQ, because I mean, if all we saw was MN is greater than PQ, well, that could be two separate line segments for all we know. So I guess maybe it doesn't matter. It's so I guess they don't need to state that. But all right, so they put the given. Now then they add NP to both sides, addition property of inequality. Then they do the segment addition postulate. MN plus NP is equal to MP, and NP plus PQ is equal to NQ. And that's what I'm saying. Like to me, in order to make this statement, you had to, one of the givens was this. To me, I'd have two givens. Because if someone was reading this without a diagram, because that's what we're given in what the diagram shows, they would say, well, where did this come from? For all they knew, we had MN and PQ to start with. So I don't know, but all right. Now, so from there, they say that MN, they use substitution. MN plus NP is equal to MP. NP plus PQ is equal to NQ, so MP is greater than NQ. Okay? The final reason may come as a surprise. However, the substitution axiom of equality allows you to replace a quantity with its equal in any statement, including an inequality. That wasn't surprising at all. Mn plus Np is equal to Mp, so you just replace Mp here. Np plus Pq is equal to Nq, you just replace Nq here. And you're left with what you were looking for. All right, another tip for a proof. General rule, the final statement of the proof is the proof statement. Well, yeah, of course, that's what we've been talking about. See the last statement in the proof of example 6. Okay. Study this proof, noting the order of the statements and reasons. So given that ray ST bisects angle RSU, ray ST bisects angle RSU, ray SV bisects angle USW. So with that, prove that the measure of angle RST plus the measure of angle VSW is equal to the measure of angle TSV. All right, so what you can do here is say that by the definition of bisect, that means angle RST is going to be equal to angle TSU, and angle USV is going to be equal to angle VSW. Start by saying that. And then just use, you got to go through the proof, but you could say that, use the reflexive property, this is equal to this is equal to that, and so let's see how they do it. They state the bisection. So based on the bisection, measuring RST is equal to measuring angle TSU. They state the bisection again, then they state what's equal. Then they do so measuring of RST plus measure of angle VSW is equal to the measure of angle TSU plus the measure of angle USV. Yeah, that makes sense. Just with the reflexive property, if this is equal to this, then that's equal. Like if A is equal to B and B is equal to C, then A is equal to C. That's how they can work all this out. Then they use the angle addition postulate because we've got adjacent angles. Yeah, so again, we could prove this informally, and this wouldn't be hard at all. But you can see how the idea of how they go through these rigorous proofs. But, we're not going to spend too much time understanding exactly how they do this. It's kind of like, so if this is angle A, angle B, angle C, angle D, okay, we're trying to prove that A plus D is equal to B plus C. That's what the proof statement says. That's what we're trying to prove. Okay, what we're given that ST bisects RSU. So we're given that A is equal to B, and then we're also given that C is equal to D. Okay, so we can, if we take B and substitute B for A here, B plus D, and then, okay, we've got B here. Now we can take D and substitute that for C here. There you go. Right? Now, that's the issue with that is that that's not an official math proof, but you can see how we can informally, as non-mathematicians, we can prove this to ourselves. And so we're not going to spend too much time going through these precise detailed analysis of how they make proofs throughout this textbook.